there. It just takes 1 minute to go fully live, and then okay, so we're live. We shouldn't say anything funny. It's just 30 seconds. There you go. And go back to the presentation. There. You guys see the presentation. Just wait until it becomes officially 3, and then okay, I don't know why my video froze, but let me try again. Okay, can you hear? Did I freeze now? So hi, Angela. Okay, so welcome back everybody again, once again, for our online SPICE-SPIN+X seminar. This time without a hiccup. So I'm Jairo Sinova and organized this series together with Liber Schmeckiel and Angela Wittmann here in Mainz, Carina Versus City, now based in Duisburg, in cooperation with the SPIN+X Collaborative Research Center led by Martina Schliemann and Burger Hillebrands in Kaiserslautern and Matthias Chloe here in Mainz. As you guys know, this is a Zoom webinar, so please raise your hands or write something in the chat if you have a question. And also please check our schedule. As you know, we don't have every week now. We tend to have pretty regular ones, but also because of the conferences, we try not to overlap the talks with the conferences. It is my pleasure and our pleasure, actually, to welcome Mirko Cinchetti back to Rheinhessen Rheinland-Pfalz conference workshop here, or talk. He's the head of the group in TU Dortmund University, and he was, of course, his PhD was here in Mainz, and then afterwards he didn't go too far. He went to Kaiserslautern in the group of Schliemann, which is also here in the audience, very proud, smiling on him. He's a specialist in many cutting-edge parts of experiments and techniques, particularly time-resolved optical, magneto-optical spectroscopy, and particularly molecular systems, where he has actually made a big reputation for himself. And he actually was given the prize for the in the Hans narrative for the best thesis as one of the awards that he has. I think he has several others. And with that, I'm going to stop sharing, and please ask you to go ahead and Mirko to start your talk, and whenever you start sharing, we will mute ourselves and turn off our cameras to give you more bandwidth. Okay, thank you.
Yes. So do you see my screen?
Yeah.
Okay, so let me arrange this. So I guess everything is set now, I guess. Perfect. So thank you very much, Jairo, for the introduction, and of course also to all the organizers of the seminar for inviting me. So before I start diving into the main topic of my talk, I would like to give a brief overview of the main activities of my group, which focus on spin-related phenomena. And the overarching goal of our group is basically to use elementary excitations such as phonons, magnons, and excitons, and their interactions to achieve optical control of quantum materials. To achieve this goal, of course, it is very important to select a suitable material platform. And this slide shows the main system that we have been working on over the last 4 years here in my group at TU Dortmund. So one intriguing possibility to achieve this goal is to exploit proximity effects. And it turns out that these proximity effects are particularly strong and important if you start with a ferromagnetic substrate and deposit a molecular layer on top. In fact, recently we have been able to demonstrate that the extreme optical tunability of C60 molecules can be used to achieve a 60% modification of this gigahertz spin precession frequency in an underlying cobalt film. We are putting this on the archive soon, and we will also present this work at the Ultrafast Magnetism Conference in September if you are interested. Another class of materials that we have been intensively studying are bulk antiferromagnetic dielectrics. And antiferromagnets, you probably all know, have attracted a lot of attention recently because they exhibit spin dynamics in the terahertz range, which it could also be useful for applications. In this category, we have studied manganese telluride, which is a charge transfer insulator, and recently also have been shown to be an altermagnet. And here, our main idea was to exploit the spin charge correlations in this material to optically generate terahertz spin dynamics. We also studied nickel oxide, which is a Mott insulator, and this material has a very sharp excitonic feature in the optical absorption spectrum. And this exciton is actually coupled to a magnon. And what we have been able then to show is that if you excite nickel oxide in resonance with this exciton magnon, you can enhance the amplitude of terahertz and gigahertz magnons in this material. So the other class of materials that we are intensively studying are two-dimensional antiferromagnetic semiconductors, such as the transition metal PS3 family and chromium sulfur bromide. And of course, here going into 2-dimension is interesting, both for miniaturizations, maybe in devices, but also, and what is more relevant for us, also for a fundamental point of view, to study equilibrium magnetic phenomena in reduced dimensions. So in my talk today, I will focus on our work on the TM-PS3 family. And in particular, in this talk, I would like to introduce the concept of DD excitations and show you how we can understand them and use them to generate terahertz spin dynamics in this class of material. And in particular, I will focus here on the iron PS3. Okay, so what are DD transitions? So you probably have already heard about DD transitions or DD excitations. These excitations are actually ubiquitous in solids that are ionic and contain transition metal ions, and are responsible for a variety of phenomena. Yeah? For example, they determine the color of transition metal oxides, but are also responsible for the catalytic properties of their surfaces. In molecules, you may have heard about spin crossover complexes. It is a DD transition that makes the transition between a low spin state and a high spin state in this kind of materials. Recently, it has also have been suggested that DD excitation may also play a role in the onset on superconductivity in copper oxide-based perovskites. On the other hand, if we go now to the materials, especially in the TM-PS3 family, DD excitation have been used recently to generate a various kind of phenomena, such as electron phonon bound states and terahertz magnons in this publication. So as you can see, there is a very rich phenomenology connected to DD transitions, but from a microscopic point of view, these excitation are, at least to my opinion, still kind of a mysterious objects. And in this talk, I would like to highlight some of the open questions regarding the nature of these transitions and hopefully also answer a few of them by using the TM-PS3 family as a model system for studying these phenomena. Okay, so let me set the stage and introduce this class of materials. These are actually transition metal phosphorus 3-phosphates. And this is a very nice class of materials, which can be used also as a model system, because if you use here different transition metals, you can see you can use a compound with iron, nickel, cobalt, manganese, but also other transition metal. You can generate a family of compounds that are all semiconductors and all antiferromagnets. And this table shows then that depending on which transition metal atom you choose, you can tune the band gap from 1.5 to 3.5 electron volt. But also you can change the Néel temperature from 80 to 160 Kelvin. And also, very interestingly, you can change the intra and interlayer coupling. So as a result, these systems offer the possibility to study different models that describe magnetic ordering in 2 dimensions, ranging from to the Ising model to XY and to the Heisenberg model. The crystal structure of the materials is depicted on this slide, which is taken from the literature. So you see here the transition metal are sitting on the hexagonal lattice, and then on the top and of the bottom of this hexagon, there are these B pyramids, which are tilted with respect to each other, while the phosphor and the sulfur atom are sitting. Yeah. So if you look from the side and you connect the phosphor and sulfur atoms, you obtain this octaedral, where in the middle you have your transition metal. And this configuration will become important in a while. From the magnetic structure point of view, we have here the magnetic moment here is carried by the transition metal, the transition metals, and we observe here three types of antiferromagnetic order. Yeah? We have other zigzag antiferromagnetism in nickel, cobalt, and iron PS3, and Niel antiferromagnetism in manganese PS3. Yeah? Nickel, cobalt, and manganese have a ferromagnetic interlayer coupling, as you can see here, while the iron PS3 has an antiferromagnetic interlayer coupling. Regarding the magnetic anisotropy, iron PS3 has an out-of-plane, yeah, while nickel and cobalt has a weak easy-plane anisotropy, and manganese PS3 has a competition between easy axis and easy plane anisotropy. So you see we have here a very rich magnetic behavior, although we are still dealing with antiferromagnetic 2D materials. So what about the de-excitation in these materials? These excitation were studied already in the 80s using optical absorption spectroscopy, but not in the context of magnetism. Yeah? So the figure here shows the optical absorption spectrum of iron PS3. You see here at a photon energy of around 1.5 electron volt, we have the onset of the band gap. But even below the band gap, we have this peak, which can be fitted, and this peak corresponds to the basically to the lowest energy DD transition in this material. So this is a transition which happens below the band gap energy of the material. And this is only the first one. There are also higher energy DD transition. They are depicted here in this table, which is taken, has been put in together using the data already present in the literature. So in the rest of my talk, I would like to closely examine this kind of transition and address several questions. Yeah? Can we understand these D3 transitions from a microscopic point of view? Then what is the excitation and relaxation dynamics? And what is the effect of the D transition on the excited state dynamics of this kind of 2D antiferromagnetic materials? And of course, in order to answer these questions, we need to go beyond using optical absorption spectroscopy. So we need to define the experimental methods that will allow us to explore this kind of questions. So this leads me to the first part of my talk, which is on the experimental methods. We have been establishing these methods since I moved here in Dortmund 7 years ago. We have now these two complementary experimental methods running in our lab. On the one hand, we have the time-resolved magneto-optical spectroscopy setup and a time-resolved angular-resolved photoelectron spectroscopy, or also ARPES setup. So both experiments are based on a pump probe technique. So we use a pump laser pulse, which is typically tunable in the whole visible range, 0.5 to 3.5 electron volt, to excite our system to generate elementary excitations. And then we use a probe pulse to detect the generated dynamics. And of course, in the magneto-optical experiments, we detect either the reflected or the transmitted light from the sample, which provide us information about the electronic, lattice, and also magnetic degree of freedom. While in the time-resolved ARPES experiments, we analyze the photoelectrons that are emitted from the sample, from the probe pulse, and these photoelectrons give us information about the spectral function, which contains information about the electronic excitations, such as excitons. Yeah? today I will show you that ARPES not only give us information about excitons, but can also be used to investigate the transition. Yeah? So this will extend the already impressive range of time-resolved ARPES application. So before I show you the data, I would like to show you a few more details about the experiments. So regarding the magneto-optical setup, I also would like to mention that our sample is in a cryostat. So for Kelvin cryostat, we can apply an out-of-plane magnetic field of up to 9 Tesla, which is very important if you study antiferromagnets. And then the detection, so we detect the reflected or the transmitted light from the sample, as you can see here. This is done using a balance detector, which is connected to a high-frequency digitizer. Yeah. So with this scheme, we can measure the reflectivity, but also the rotation of the probe polarization. And by modulating now the pump pulse using an electro-optical modulator, we can achieve also high sensitivity in the measurement of the polarization rotation. Yeah? We achieve here a sensitivity of about 70 microdegrees. And here you see the modulated and unmodulated signal, and you see that by doing this modulation, we have a much higher statistics. So the degrees of freedom that we measure, I already mentioned, electronic and lattice by measuring transient reflectivity. And of course, if you want magnetic information, typically what you do is you measure also the rotation of the polarization of the pump beam. The time resolved ARPES is shown, setup is shown here. This is also a pump probe setup with the difference that now in the probe beam, we have to generate high harmonics. So we focus our laser in a gas jet, and this allows us to generate high harmonics of the fundamental up to 70 electron volts. And these high photon energies are needed because we use the probe photons now to photomeet the electrons. And these electrons are then analyzed using a so-called momentum microscope. So what is the advantage of using such a momentum microscope? Here you see what we can measure with this instrument. And we perform some characterization measurements on another 2D material, which is tungsten disulfide. And here you see first what we can do in a static experiment, so without the pump beam. So with what we measure in the photoemission experiments is basically the photoemission intensity, which is given here in this gray color scale, as a function of the momentum of the electrons in the plane parallel to the sample surface. So we have here the whole photoemission intensity in the whole Brillouin zone. Here what you see are these circles that corresponds to the K values of tungsten disulfide, which are actually quite famous in the context of valletronics. So we can really image these points in one shot. So we collect then this data cube of so-called momentum maps. So we record these images as a function of the kinetic energies of the photoelectrons. And then if we cut them along a high symmetry direction, what we obtain is the band structure of the material. So here you have the momentum along one particular high symmetry direction. And here is the binding energy of the electrons. 0 here is the valence band maximum. And what you see here are then the bands of tungsten disulfide. These two spin-orbit split bands are actually quite famous. Energy resolution and momentum resolution are given here. Now, if we do a time-resolved ARPES experiment, so now we also excited the system, for example, at 1.2 electron, with a photon at 1.2 electron volt. So now we not only see the occupied, so the bands below the valence band maximum, as you can see here, but we also see photoemission intensity in the conduction band. You see here that 0 is the valence band maximum. The positive energies here means that we are in the conduction band. And if you look here at the momentum map recorded at 1.5 electron volt above the valence band maximum, you recognize that we have very distinct features, and these correspond to photoexcited electron now in the sigma and K values of this tungsten disulfide. And now we can plot the intensity as a function of the time, and we can see how the population, for example, in this case, decays from the K value to the sigma value and also calculate, for example, relaxation time scales and so on. The energy resolution when we do the time result experiments is a little bit higher, so 100 millielectron volt, and the time resolution is about 50 femtosecond. Okay, so now I introduce the methods. Let's go back to the transition metal phosphor trisulfides materials and first study the electronic ground state using ARPES. We performed the experiments on freshly cleaved crystals in UHV at room temperature. And what you see here are the momentum maps that I introduced before, recorded at different energies of the electrons. The energy is always referenced to the valence band maximum. What you can see in these images is that we have an hexagonal symmetry of these momentum maps, and this is good because the Brillouin zone of these, the surface projected Brillouin zone, which is what we see in our experiment, has also an hexagonal shape. So now we can again cut these stacks of momentum maps along high symmetry directions and have a look at the band structure of this material. So this is the band structure now along the gamma K direction. You see here for iron, nickel, and manganese PS3. And you see that actually the band structure, at least at a first glance, looks kind of similar. We can also have a look at the band structure along the gamma M direction. Also here we have a similar behavior of the bands. And in particular, at least for the iron, cobalt, and manganese PS3, they have a very similar behavior. We have 3 groups of bands that you can also recognize here in the angular integrated intensity. You see we have here a minimum and here another minimum. So these minima distinguish these 3 groups of bands that are separated by a small in gap. Okay, so now, of course, if we want to understand this band structure, we need also some support from theory. And the calculation were done by the group of Jose Baldoví, who gave actually the seminar last week. And they used DFT plus U calculation to calculate the band structure to compare with our experiments. And first of all, this is always what we do. We first check that more or less we have a good agreement between theory and experiment. In fact, the experimental band structure here was used to fix the U parameter in the DFT calculation, DFT plus U calculation to an effective U of 1.9. And you see that not only the band structure fits quite well, but also the momentum maps. But the most important thing that we can do now with the theory, or that they can do, is actually to calculate now the to project the density of states or the bands on the various atoms in the iron PS3. So here you see the bands projected on the d orbitals, the p and the s orbitals. And sorry, the iron d orbitals, the phosphor p orbitals, and the sulfur p orbitals. And the important thing that I would like to stress here is that the top of the valence band is formed mainly by the 3D states of the iron in the iron PS3. Okay, so since the valence band maximum and also the conduction band minimum, which I didn't show, are mainly formed by the iron 3D orbitals, first of all, what I didn't say is that this can be then understood as a Mont-Hubbard insulator. But we can actually use also a simplified model to understand excitation of this material when we use photon energy that are more or less in the range of the band gap. So in order to understand what happens when we optically excite the system, we can describe actually iron PS3 as ionic crystal. So we have iron 2 plus and then PS3 2 minus. And the states that are actually responsible for the excitations at these low photon energies are basically electronic states that are localized on the iron 2 plus ions. So in this context, we can understand the D transitions as excitation of our iron 2 plus multiplet. So we have these localized iron 2 plus ions where we have 6 3D electrons. And when we excite the system with photon energy more or less in the range of the valence gap, we can think that we are exciting the electron only in this iron 2 plus ion and forget, at least in a first approximation, the ligands. This kind of description is actually not new, but it was introduced already and discussed lengthy in the 80s. Yeah, this is only one paper that discussed this kind of approximation, where you see here, this is the range, the valence band maximum, in this case for nickel PS3, where we see that we have these localized nickel states that are merely responsible for the bands formed at the valence band maximum. Okay, so now that we are concentrating on the iron 2+ multiplet, we can first determine the ground state. Yeah, this is basically easy. You have an iron 2+ ion in an octahedral crystal field. So of course, the crystal field leads to a splitting into T2G and E2G level. And the important energy scales here are the crystal field energy and the exchange energy. The exchange energy is actually larger than the crystal field, and then you can fill in your 6 electrons, and you end up with a state with 4 ampere spin that we can also notify as 5 T2G state. So this is the ground state. Now, what are the excited state of this multiplet of 3d6 electrons? So these are basically, these excited states correspond to our DD transitions. And here you see all the energy of the various DD transition that I was introducing before. If we concentrate on the first one, yeah, this first, of course, this excitation are an excitation of a multiplet of 6 electrons, but okay, but you can always think about this transition. They will be made of, they will have contribution of single particle excitation. And the first transition, actually, the largest contribution comes from this transition from the T2G to the AG state, to the AG orbital. So basically, when you do this transition, you are modifying the crystal field. Yeah. And this will generate a Jahn-Teller distortion of the ligands. And we can expect that this will lead somehow to a generation of some kind of phonon modes in our crystal. The second transition goes from 5 to 3. This means that you are also flipping a spin. So you're not only generating phonons in this case, but presumably you can also use this transition to generate some kind of spin dynamics, for example, magnons. So this is actually what I find exciting about iron PS3. Is that it hosts this kind of excitation, which can ultimately thought as being localized on a single iron 2+ ion. And these are basically zero-dimensional excitation, so localized on an atom, but that might be used to generate lattice and spin dynamics in a 2-dimensional system. And now let's see if this is actually the case. So if we can do this, yeah. And I will start with the Magneto-Optical experiments. We performed a bunch of experiments using excitation below and above the band gap, yeah, that are reported in these two papers. Today, I will discuss only the experiments with below band gap excitation. And we use either crystals or also exfoliated flakes on HBN that were also produced in the University of Valencia by the group of Eugenio Coronado. Of course, if we use the flakes, we have also to characterize them, for example, determine the thickness, but also using Raman spectroscopy, check that they are also intact so that they have the same Raman spectra as the bulk crystals, and this we did. And then if we want to study them in our setup, we also have to implement some kind of microscopy. So we use this kind of microscope objective that allows us to get a lateral resolution of about to 1.5 microns. So then the experiments are done by pumping the system below the band gap, yeah, with a photon energy in the range between 0.9 and 1.1 electron volt, and probing with a photon energy which is more or less slightly below the band gap. And at the temperature of 10 Kelvin, which is below the nil temperature. So this is what we see in our experiment. So this is the typical, here we have the rotation of the polarization of the probe beam as a function of the delay. And these curves have an incoherent background. So you see a decay and then a recovery. But then superimposed to this incoherent part, we also have these oscillations. And if we do the Fourier transformation, we see that these oscillations have a frequency of 3.2 terahertz. If we have a look at the Raman spectra, we see that this frequency corresponds to an optical phonon mode, where basically the iron 2+ atoms and the ligands are displaced as shown in the figure here. Okay, so now let's have a look at how the amplitude of this optical phonon depends on the pump photon energy. Yeah, and this is this curve here. And what you see here is that the amplitude follows very nicely the optical absorption spectrum. And actually, we see even here a double peak structure in the amplitude, yeah, which actually correspond to the degeneracy of the DD transition due to the distortion of the ligands. Yeah. So basically what we observe is that when we are in resonance with the DD transition, we have a strong enhancement of the amplitude of this phonon mode. So as I was assuming before, we have a first demonstration that we can use DD transition to generate lattice dynamics. So let's have a look now at the temperature dependence. Yeah. Now we measure the same curves, but as a function of the temperature, and plot the phonon amplitude as a function of the temperature here on the right. And you see that here, for two different photon energies, you see that in both cases, the amplitudes goes to 0 as soon as we cross the nil temperature. Yeah. So somehow these phonons feel the magnetic state of our crystal. And why is this the case? This is the case because when you go from the paramagnetic to the antiferromagnetic phase, you have a doubling of the Brillouin zone. And basically, the M point of the paramagnetic phase is collapsing into the gamma point of the antiferromagnetic phase. And basically, this zone boundary mode becomes then optically active when they are now in the center of the Brillouin zone. And this is what it's called actually a zone-folded phonon mode. Okay, so up to now, I've shown that we are able, if we excite the DD transitions, we are able to generate optical phonons, and these phonons somehow feel the magnetic state due to the fact that they are zone folded, yeah, due to this kind of zone folding. What about the spin dynamics? Yeah, if you look in the literature, it is reported that this phonon mode actually hybridizes with a magnon mode, yeah, in the presence of a magnetic field. Yeah. So the idea that we had now was to exploit this hybridization to see if we can also optically generate this kind of composite excitation, which consists of a magnon hybridized with a phonon. So the thing that we had to do was to repeat the experiments, but now as a function of an applied magnetic field. Yeah. And these experiments were done on crystals for stability issues instead of on the flakes. And we see the same oscillations that we see also in the flakes here at 3.2 terahertz. This is the mode that we are interested in. And now we do the same experiments, but now for different applied magnetic fields. Yeah? And if you look here at the spectra, at the curves, that we recorded at 9 Tesla, and we do like a Fourier transformation, we see that now we don't have only a single peak at 3.2 terahertz, but we have this peak is split in two. Yeah, and this would be the lowest, the two branches of this phonon-magnon polariton that we are generating in the presence of the magnetic field. Yeah, we can follow the magnetic field dependence of the frequency of the lowest branch of this phonon-magnon polariton, and this follows. This follows what also was reported in the literature from the Raman spectra. So we have this behavior. So basically, the point here is that by using the DD transition, we are able, and an applied magnetic field, we are able to generate a hybrid phonon-magnon mode at 9 Tesla. Yeah. So this is the story so far. So I showed you now what happens if you excite iron PS3 in resonance with the first DD transition, yeah, which is this one, that modifies the crystal field and somehow generates these optical phonons that whose amplitude basically increases when we are strongly enhanced when we are in resonance with the DD transition. And then I showed you that by applying the magnetic field, we can hybridize these phonons with a magnon and detect this hybrid magnon phonon polarity. So far, we have observed the effects of exciting the DD transitions, including the generation of both elementary but also composite excitation. Yeah? But at the moment, we still lack insight into the microscopic nature of these excitations. And to gain this insight, what we will do now is to implement the time-resolved ARPES experiments. So we have performed two sets of experiments, one with excitation below the band gap, so basically exciting only the first DD transition, and one set of experiments with above band gap excitation, which will basically excite not only the first, but also the second DD transition. The pump photon energy is 1.2 electron volt and respectively 2.4 electron volt. So let me now explain you what we see on this slide. So these are the momentum integrated, this is the momentum integrated photoemission intensity that we measure in a time-resolved experiments when we excite iron PS3 below the band gap. You see here that we have this enhancement of the intensity of the photoemission intensity around 0 femtosecond. So this is when pump and probe overlap. Yeah, and this plot basically gives you the density of states of the excited state. Yeah, so this energy here is the energy scale corresponds, these energies are the energies above the valence band maximum. So if without optical excitation, we will have no intensity above the valence band. Yeah, but here that we see intensity, it means that this intensity comes from the excitation. Yeah, and what we see here is a kind of density of states, yeah, of the transient population of the states as a function of the time for the different states above the valence band maximum. So we are here sensitive to the excited state dynamics. If we have a look now at the momentum distribution of the photoelectrons in our experiments, so the slide before, I showed you the momentum integrated maps. Now here I show you the momentum maps that we record at a particular energy. For example, 0.3 electron volt above the valence band. Yeah, you see we have a very distinct momentum distribution of our photoelectrons. And this distribution correspond very nicely to the same pattern that we observed for the ground state at an energy of 0.8 electron volt below the valence band maximum. Yeah. So the energy difference between these two states is exactly 1.1 electron volt, which is the energy of the first DD transition. So we take this as a first hint that actually what we see in the time-resolved ARPES experiment is a fingerprint of this excitation. And in order to, yeah, of course, this is just a first hint. We need something more, more quantitative. So we asked our colleague, Fridtjof Anders here at TU Dortmund, to calculate the equilibrium spectrum of the lesser green function, which basically correspond to what we would see in an ARPES experiment from our iron 2+ multiplet in the ground state, and then also to calculate the spectrum of the excited state. So when we excite with 1.1 electron volt. Yeah? And you see that basically these two green functions, basically many of the peaks here overlap. Yeah? So this gives us another argument, yeah, to expect that what we see in the ARPES for the ground state and for the excited state looks the same. So putting these two information together, we our interpretation is that indeed, in our time-resolved experiments, we can see a fingerprint of the localized transition in our transient signal. Of course, there are still a lot of things that we need to understand and also how to extract, since we have these very nice momentum maps. The idea is now to exploit this angular distribution, also to learn even more about these excitations. But we can already do something. For example, we can have a look at the time scale of the relaxation. So first of all, we see that the excitation is more or less instantaneous. Instantaneous in this case means that is below within the resolution of our experiment, which is 50 femtosecond. Then we can also have a look at the lifetime of this excitation. And here we find a surprisingly short lifetime of 83 femtosecond, which is actually unexpectedly low for a localized atomic-like transition. And this gives us an indication that the hybridization between the iron bands and the sulfur and phosphor bands, although minimal, must be considered to fully understand the relaxation dynamics of these excitations. Moreover, if we compare now the lifetime to the line width measurements, so 83 femtosecond would correspond to a homogeneous line width of 48 milli-electron volt, which is actually a factor of 3 to 4 times narrower than what we measure actually in the optical absorption experiments. You see here we have line width of above 250 milli-electron volt. So why there is this discrepancy? This can have two reasons. Either that the optical measurement have additional inhomogeneous broadening. You have to consider that the optical absorption experiments are more bulk sensitive, while the photoemission is surface sensitive. So there might be some mechanism of inhomogeneous broadening in the bulk, or there could also be some additional quasi-elastic scattering channel that we do not detect in the photoemission experiments. Okay, now let me come to the last part where we did now the same experiments, but now exciting the system above the band gap. So here we have much more information in this kind of transient ARPES signal bands. You remember this is basically the transient occupation of the bands. And we see if we take here if we integrate overall the energy, if we integrate these curves, we see here that we have at least 3 main features in these line profiles. And this corresponds to various excited states that we are observing in this experiment. The first state that we see is the conduction band. This is very, very low intensity, and it seems to decay very, very fast, which actually we do not fully understand. Then we have a signal at 1.1 electron volt above the valence band maximum. And this, by using the same argumentation that I showed you before, we can ascribe it to the second DD transition. So this is the spin, not spin conserving transition from 5 to 3. And you see that this here, the time evolution has a non-monotonic, it has at least 2 exponents here. And we can fit this with a double exponential decay, and we find 2 time constants. One is 50 femtoseconds and one is 1200 femtoseconds. And then at lower energies, at the same energy as we did in the previous experiments, we also see the fingerprint of the first spin conserving DD transition with the same time scale that we observed also before. So these experiments are really consistent with each other. So what can we learn now from this further experiment? Well, we see that this spin forbidden transition from 5T2G to 3T1G has a double exponential decay. And this indicates the presence of 2 independent decay channels in the relaxation of this transition back to the ground state. And basically, these 2 pathways have a decay constant of 50 femtosecond and 1200 femtosecond. And here you see how we associate these two relaxation paths. Yeah, one would be a virtual hopping between neighboring sites. So some kind of exchange mechanism, and then a spin orbit mediated spin flip process with the longer time scale. So to rationalize a little bit better the time scale related to the spin orbit coupling mediated spin flip process here, we asked Jose to calculate the spin orbit constant. Yeah, so they started from the electronic band structure and then determined the spin orbit constant for the irons 2+, and they get here this value of 14 millielectron volt, which corresponds more or less to 300 femtosecond, which is kind of in reasonable correspondence to what we observe experimentally, so time scale of hundreds or at least or even thousands of picoseconds. Moreover, this spin-orbit contrast makes also sense, and also makes sense to interpret the data like this, because actually in nickel PS3, a similar value of this spin-orbit constant was actually deemed to be sufficient to mix these E1G and 3T2G's excited state, and this mixing then enables also spin forbidden DD transition. Yeah, so basically here we have the same interpretation for our data. So the spin orbit coupling would mix the 5EG and the 3-1G states, and in this case then we will be able to basically get our spin orbit coupling spin flip on a time scale of the spin orbit constant. Okay, so you can see that doing these time-resolved experiments, ARPES experiment, give us a lot of information about this DD transition. The last thing that we can read out of our data is that when we excite above the band gap, we have instantaneous excitation of the conduction band. And then the spin allowed and the spin forbidden transition, they come with some delay with respect to the excitation, and the spin allowed transition exhibit a quicker buildup, 22 femtoseconds, compared to the spin forbidden that actually builds up in around 50 femtoseconds. So I hope I showed you that actually using time-resolved ARPES is a really nice method to get also a fingerprint in momentum space of this kind of localized transition. And we can detect not only the transition below the band gap, but also the one above the band gap, and we can access the ultrafast dynamics of this excitation. Of course, as I said, there is still a lot of things that we need to understand, and for this we need also theory support. For example, there is a lot of information here in this momentum distribution of the photoelectron that we would like to also exploit to learn even more about this phenomenology. So this brings me to the conclusions. I've shown you today our work on the iron PS3 and what happens when you excite these zero-dimensional atomic-like DD transitions in terms of generation of hybrid phonon-magnon mode, but also in terms of how this kind of transition evolved in time and how they decay again to the ground state, which is possible by performing time-resolved ARPES experiments. These results are published in these papers here, and the last part on the photoemission experiments is on the archive. Before I conclude, I would like to thank our collaborators. These are on the left part here. There are the collaborators on the part on the transition metal PS3 materials. First of all, I would like to mention Clara Saraceno, that with whom we have a collaboration in the building F-femtosecond XUV sources. And then for the TMP3 studies, I mentioned already Fridtjof Anders, then Alberta Bonanni, Jose Baldoví for the theory support, Eugenio Coronado also for delivering the samples. Davide was here in Dortmund, and we started together a TR160 project on these 2D materials. and Sasha, we had to unfortunately terminate our collaboration due to political reasons. These are the people of my group that performed the experiments. Yona performed the photoemission experiments on the ARPES-3. Fabian already graduated on his thesis on the magneto-optical studies of ARPES-3. And Umut is now a postdoc in the magneto-optical setup part of the experiments. This is a photo of my group, and I would also like to mention 3 postdocs that were heavily involved in the development of the time-resolved ARPES experiments. Giovanni, who is now at Unigraz as a professor, Stefano Ponzoni, who has now a permanent position at École Polytechnique, and Matthias Supar, who is now working in the industry. Last but not least, financial support from the Merkur Stiftung and this cooperation project, then DFG TRR 160, who was now terminated, my ERC Consolidator grant, and the Sinfonia FET project, And with this, I would like to conclude and also advertise that if you are interested in this kind of experiments, please contact me, and we have PhD and postdoc positions in our group. So thank you very much for your attention.
Okay, thank you very much, Mirko. So now we are open for questions. Please raise your hand or write it in the chat if you would like to ask some questions. I may just start it off a little bit from the point of view of this control aspect that you were mentioning. So in the fast relaxation, that the fast spectroscopy that you're having in there, are you able to control the particle densities at different energy scales well and understand how the decay process is fully, and then control it through strain, or just at the moment it's more spectroscopy-wise?
Well, I mean, control in this case is more, as you can see here, you can basically control the amplitude of the phonon mode by just selecting the proper photon energy. Yeah.
Okay.
This was, in this case, what we have achieved in terms of control. What I didn't show, for example, is that you can also change the amplitude of the phonons by changing the polarization of the pump, for example, this kind of optical control, if you want, of this kind of modes. Then, of course, what you mentioned is mainly what happens, if I understood correctly, what happens if you increase the intensity of the pump. Yeah. And there we didn't do yet experiments, but this is something that can for sure be done. For example, it is known that in other 2D materials that you can go from in a range where you have excitons, but then if you increase the intensity too much, then the excitons start to interact with each other, and then you have basically they decay into single particles. So this probably can also be applied to this kind of DD transitions. Yeah.
Cool. So let's go to Thomas Matelli. Go ahead and ask your question, and Milton. Yeah.
Hi, Mirko. Thank you very much for a nice talk. I have a question/comment about comparison of time-resolved ARPES dynamics and the bandwidth which you observe in ARPES.
Mm-hmm.
Wouldn't time-resolved ARPES relate mostly to the population dynamics, while when you measure static ARPES, you see spectral function, which is a different kind of property? Can you comment on this?
Yes, but I mean, in principle, what you measure, like if you do a 2-photon photoemission experiment, yeah, you measure lifetime. Yeah, when you measure a lifetime, of course, you have different part of the lifetime. Yeah, you have the one due to electron-electron scattering, for example, but then you also have electron-phonon, electron-magnon, and so on. And the question is, what do you see then in the photoemission? This depends also on the energy resolution of your experiments. Yeah. So what I was mentioning is that one possibility why we see in the ARPES experiments longer lifetime than in the line width would be that in the ARPES we don't see some relaxation channels. So
yeah, what I think is, what I wanted to say, basically, in ARPES, in time-resolved ARPES, you would see, let's say, distribution functions. So you would see how density
Yes, yeah.
changes with time, and this is not related to quasi-particle property, which is spectral function, which you see in ARPES. These are two, they are connected, but they are quite different things. So one is, let's say, longitudinal relaxation time, the other one is transverse relaxation time, if we talk in terms of
T1 and T2, yeah. Okay, yes. I think, yeah, I think it's not easy to give a very short answer, but yeah, thanks for the comment. For sure, it's always tricky to compare optical absorption and photoemission. Yes, you are right. Yeah.
Okay, thank you. Bye.
Thank you. Martin, go ahead and ask a question.
Thanks, Mirko, for these nice and interesting results. Just a few words before the question we just had before. It depends critically on the excitation. When you have carrier scattering or the relaxation, then of course you measure the ensemble dynamics and not the single particle dynamics. But when the intensity is not high enough, then you have measure really the single particle dynamics, how they relax the ensemble to the ground state. But anyway, my question is also time-resolved ARPES. The last experiment, what you have shown, this double exponential decay, you had one with the transfer to the other side, which was fast, and the slow one includes a spin flip. You can only have a double exponential decay when one channel stops. Why should the first channel suddenly stop?
Yeah, this is why I said that this can be interpreted, but only considering that we have two independent relaxation channels. Yeah, so yes.
They are independent. You also have, when you have a single electron, it can scatter with other electron, it can scatter with phonons, but the electron is so strong that you cannot see the other, and it decays completely to zero before the other one has any participation. That should also be here the case.
Yes. To be honest, this is, I know I was thinking about this, but at the moment I don't have a better explanation. Yeah.
When you can have a double exponential decay when one counts for the hole and the other for the electron, but you cannot measure that with ARPES.
Well, I'm not so sure about that. It depends.
Okay.
Yeah, but thank you. I know. Yeah.
Cairo, you were...
So Deepak Jana, I think I see if he can actually join us in this thing. It's, yeah, he's rejoining and he's going to be able to ask his question directly. He's written it down in the Q&A, but I thought it would be best that he can come online. Okay, Deepankar, can you unmute yourself and ask a question, or do you want me to read it out loud? Depends on whether you can or not. Okay, so let me read it for you. So thanks for your talk. And can you please elaborate the equivalence between the band model where FEPS3 has a finite band gap on the molecular orbital model when DD transitions is considered? In one slide, it is shown that the band gap is 1.4 electron volts, while there is a sub-band gap DD transition.
Yes.
That means that the DD states are not involved in the band formation.
This is indeed a very, very good question that I asked already also many theoreticians. And I mean, it is kind of tricky. This is what I mean. What is a DD transition? Because in a band model, of course, you have only bands in the valence band and conduction band, and they are separated by the band gap. Yeah, but the DD transitions are below the band gap. So as I understand it, then you have really to look into this multiplet, and these are really local excitations that you are not present in a simple band structure calculation, so like a DFT calculation.
Okay.
But of course, yeah, this I hope that I would motivate now people also to dig into this understanding what is really a DD transition, how we can understand it.
Okay.
On a microscopic point of view.
Okay, perfect. Let's see, I don't see any more questions, so I'm going to stop 1 second here at the streaming here. and the streaming and the sharing and